All right. Thanks, Marissa, for the introduction. So I just want to once again highlight my co-authors in this piece, so Dr. Katie McFerrin and Dylan Robinson. So as Marissa mentioned, this is an MCMP funded effort. However, we're working around inlets. CIRP likes inlets too. So we feel like this might be a nice applicable talk and also might open some doors for conversations and maybe future collaborations. Okay. So no surprise to all of us in this room, right? Shoaling is very much the sediment budget surplus when these deposits end up in less than ideal locations. And so obviously that sediment surplus ending up in your navigation channel causes large issues and can lead to costly dredging operations. So while subaqueous mechanisms of channel shoaling has been largely studied extensively, the subaerial or aeolian contributions has very much been understudied. And so where that leaves us in terms of the science is that there's very few estimation tools and techniques that we can provide USACE districts, program managers, and engineers. So I like this initial photo of the sediment budget. This is from, I think, Comar 1996, right, in which we see these gains and losses of the sediment within the system. And so if we look at the wind transport component of the system, we see that wind is blowing into the dune system and quantified as the sediment loss. That is true in many points in time within a system. However, not always the case, right? So really working to challenge this paradigm and ask the question of, well, what if the wind comes along shore or in this general direction? What does that mean for the fate of my navigation channel? And this is not a problem that's unique to Port Mansfield. Here's a shot of Manasquan Inlet, New Jersey, right? Likely also facing some aeolian drivers causing issues within that system. So the study area for this talk is Port Mansfield Inlet, Texas. So you can see a map of the study area. So bounded by two jetties. North of the jetty is Padre Island National Seashore. So it's managed by the National Park Service. South of the jetty is Padre Island, which is managed by Texas GLO in terms of that land butting up against the jetty system itself. In terms of Port Mansfield, from an aeolian perspective, it's incredibly sensitive to aeolian processes. And you can see some of those sort of heavy hitters are bolded on this slide. So it's a semi-arid climate. It's relatively dry. The winds are pretty high magnitude, typically 10 to 20 meters per second, coming from the east to south-southeast. So these are winds arriving at very high oblique angles to the shore, and then also very fine sands, right? 0.12, 0.17 millimeters on average. It can get a little bit coarser, but very fine in general. And then looking more on the hydro side of the equation, and Dr. McFerrin will talk about this later in this presentation, we're in a microtidal environment, very low wave energy. A lot of the waves are driven by that wind generation. Longshore sediment transport on the order of about 125,000 cubic meters to the north in terms of transport rate. And then authorized channel depth, whenever it is dredged out, on the order of about 17 feet. However, shoaling occurs rapidly following dredging operations. And so part of the impetus for doing a lot of this work was to better quantify maybe what we can do to assist with preventing frequent dredging operations. So looking at the jetty construction history, this aerial image that you see on the screen was taken from a report during channel construction. So the channel was initially dredged in 1957 to provide access to the Gulf for commercial and recreational vessels. And since 1957, or I guess I should say immediately after that 1957 construction, a storm event immediately flanked the jetty and caused some destruction, and that an improved jetty was reconstructed around 1962. So one thing I want to point out with this slide and this aerial image, and I really like it, is taken from an old Giddy report, or an older USACE sort of report format. But if you look on this image, you can see these sort of white squiggly sedimentary bodies. Those are transverse barconodal dunes. And so as an aeolian geomorphologist, these are, I can look at this image and tell there's a lot of sand in the system on one hand. And secondly, there's a lot of wind driving that sediment across the landscape, right? These are transient bodies and reservoirs of sediment. And as you can see from the position of this newly constructed channel, that material is likely ending up within that navigation channel as well. So not very, or I guess looking back, it's a problem that we've been working or facing, I should say, in this region for quite a long time. So before or predating my time on the project, Zach Tyler within the Coastal Engineering branch was working down here. And so that the sort of plots on the right of this slide are getting at some of the desktop analysis that he performed during the opening phases of this work unit, in which he was just trying to better understand and quantify with the back of the envelope calculations of how fast was the shoaling taking place within the channel. So there you can see some bathymetric data of before dredging, immediately after dredging, and then a few surveys completed in times after that dredging event occurred. And so what Zach came to the conclusion of is within less than 2 years, you're seeing upwards of about 13 feet of shoaling taking place in that navigation channel. So quite a big issue. And yeah, so it definitely drove home the point of needing to study this inlet further. Something else to point out is that they did some preliminary hydro surveys as well as some ADCP measurements. And what they found is that the hydrodynamics within the channel and around it weren't fully describing the entire picture. And there must be some other driving mechanism in terms of enhancing that sediment transport into the channel. And so that's when the attention sort of turned towards looking at the aeolian side of the equation. And there's two photos in the upper left of the slide were taken from one of the first aeolian field campaigns at the study site. And what you're seeing is a lot of sediment has infilled those jetty stones. And then on top of that sort of sediment reservoir, we are seeing some sort of aeolian bed forms or ripple formations on it. So, very much indicative that aeolian processes are actively operating on this landscape and likely ending up in that navigation channel as well. So as we mentioned in the opening slides, this is an MCMP focused effort. So, and what I'm showing in this image is sort of like the support that's been provided since FY24. So we've been able to complete 3 aeolian specific field campaigns at the study site. So we're trying to better understand the system as a whole. So we've targeted these campaigns around certain setup conditions. So the first experiment was looking at sea breeze conditions. Second experiment was looking at high magnitude winds, so during the April and May months, sort of the time period that we're in now. And then the third experiment, which we just wrapped up in January of this year, was looking at the northerly wind direction. So how much wind are those frontal systems, if you think about westerlies propagating across the US, as those winds switch directions from the north side of the inlet, what does that mean in terms of shoaling rates? Okay, so moving forward with this portion of the talk, though, I'm going to get a little bit more into kind of how we quantify the aeolian or windblown contribution to the channel. From this work, we were able to develop a new or play around with a new methodology that could be useful for districts to use. That's currently in review. It's being put as a ERDIC tech note. And then also, Dr. McFerrin is going to talk about a little bit more about the pre and post-dredge shoal formation evolution and kind of the ongoing efforts that we have to measure those and sort of the end goal with that data collection. So looking at some of the aeolian field data collection methods. So this is the wind side of the equation. Here you can see you're using a few different instruments. So the first one I want to highlight is the Meter Atmos 41. This is an all-in-one weather station. It's got a 2D sonic anemometer in it. So this is a nice tool because it's really easy to set up in the field. You can train a tech with, I would probably say on the order of about 5 minutes. They can set up in the field and you get really good data. More traditional aeolian geomorph sort of instrumentation setup is what you see on the right of that image. That's a cup anemometer array set at log. And so from that, the spacing of those anemometers and the various speeds, we can get a good approximation of what U start is at the bed. From that, and then at the top of that anemometer mast, we see that we have another cup anemometer with a wind vane, right? So very much the more traditional technical side of aeolian geomorphology, but there's constant work to see if we can't improve our estimates of flux and transport and transport conditions with a single instrument like that Meter Atmos 41. So sort of a side, I guess, objective of a lot of our work is to better draw that correlation between more rigorous instrumentation versus can we get a similar data product with a simpler instrument for districts to use. So on the sediment side of the equation, so we care about sediment being pushed into our channel, right? And we have to factor in that beach fetch or that lateral distance that the boundary layer is getting used to the underlying surface roughness is very much a driving factor. And what that means within the aeolian realm, right, is that where you're at on the beach matters in terms of how much sand may or may not be moving. So the best way to make sure that we're capturing the maximum sediment transport rate along a transect is to deploy a series of sediment trap stacks. So here you can see we have our sediment traps set up. They're bend in different sort of intervals, so closer to the bed where there's likely going to be more sediment moving. You can see I have a bit higher spatial resolution of our trap apertures in the order of about 5 centimeters. And then as I move higher up into my saltation cloud, those sediment traps are on the order of about 10 centimeters per. So the trap stack in total is about 40 centimeters tall and then bend into those different sort of subsampling spatial areas. So each trap stack has 5 traps. Each transect line had 10 traps. So a total of 50 traps or 50 sediment samples per run were conducted. When the traps were open in the field, they were open for a time period of about 15 minutes. This is pretty common within the alien literature of getting a robust measurement of what that sediment transport rate is if you were to back calculate it out to how much sand is moving per second. And I should also note that these traps are oriented into the wind. So that transect, if wind is coming from a consistent direction, then that transect will not move. If it's moving around during the course of the study, that transect will also follow suit and move as well. And so another thing too I want to highlight with this slide is you can see just from all those traps on that table, right? This is an incredibly intensive process. In order to get to this field site, you're either taking a boat and then hiking your supplies across the jetty, being all the sediment traps, the canopy you see there, the table, right? And any sort of other equipment you might need. If you're to drive it, you're looking at a 30-mile drive from south to north if you're on the southern side of the jetty, or an 80-mile drive if you're going from north to south if you're on the north side of the jetty. So a huge effort goes into just access logistics and makes the site pretty difficult to study in general. But a huge shout out to the field crew that assisted, and they did not throw a mutiny or anything, because it's a lot of work, and I appreciate all the hard sweat and tears. So looking at the results, this is just from the first experiment, or the Sea Breeze event experiment. So here we're looking at, we got about 5 days of good field data collection, right? You can be there ready to go and all set up, and it's not raining, but the wind's not moving the sand. So you need to make sure that you are at least above that threshold of motion. And what's interesting about this data set is that we have relatively low wind speeds, right? But all the wind speeds were more or less within the same, or not within the same, but about 0.3 meters per second within each other in terms of these transport rates. But we had variable degrees of wind angles, and so it set us up uniquely to look at the driving force that the wind direction can have on shoaling rates. And so looking at just, an example of one of our transects. So this is, you're looking on the x-axis, it's a cross-shore distance. So 0 is at the high water line. And then that last trap is in advance of the dune toe. And if you recall, I mentioned that the subaerial beach is kind of what we're aiming to capture. And if we are, butting up against the high water line, then we're just outside of a moisture constraint for transport. And then if we're ahead of the dune toe, then we're not getting into maybe flow compression that might be happening as you get closer to that Stoss slope. So really just trying to bound that subaerial portion of the beach. Each one of these dots is a sediment trap stack, and we're just looking at bulk flux within each of those, right? And so I like to highlight this plot because it really drives that point home of where you're at on the beach matters, right? If I was at that third point versus that apex of this distribution, right? You can see how we would get two completely different pictures of how much sand is moving within the system. And if you are going on the field and placing your sensor in one location versus another, you just have to keep this in the back of your mind of making sure that you're at least sampling as optimal as possible. Another thing too I want to point out, this is the same transect line run multiple times. So we were able to see the impact of increasing wind speeds, what that might have in terms of the overall bulk flux at each of these locations, which were reoccupied during each run. And now some of that variability is drawn by or driven by distance. A lot of it's driven by upwind surface roughness, right? So Texas, you can drive on the beach. So tire tracks are very much common within that upwind extent. You might have some residual shell hash, buried rack piles, or even as you move further back into that transect, you're going to get more uniform ripple formations. Pencil for scaling to those photos. I feel like this is always a nice slide to throw in there. So a lot of our models, whether you're using Aeolus or the do response tool, a lot of it comes back to taking field data or some sort of data and then bringing it into an empirical model. And that's just the reality of the science, right? Field data is expensive to collect and it doesn't cover the entire suite of conditions. But I think this is a nice representation to kind of showcase where the field data fits in. Obviously, Bagnold seems to be, with this data set, seems to be the most closely related model that we could use, and the others, as we can see, overpredict in many situations. Currently working through the data from the second and third experiment to get them in the same sort of construct to see how those results fit with more contemporary or more traditional empirical models of aeolian sediment transport. Okay, so we have that field data collected, right? And we were looking at previously, bulk flux along a transect and kind of how that changes with where you're at, as well as with varying degrees of wind magnitude. But the question still was arising of, well, how do we quantify in terms of aeolian driven shoaling? So we have wind coming across this surface, but can we extract out that X component and then better quantify Q? And then more importantly, can we do that for a suite of different sediment transport conditions and wind approach angles? And so a lot of this work led to what Dylan Robinson helped develop. And ultimately like pioneered and is still helping out with as we get this tech note across the finish line and through the review process. So Dylan, if you're out there, we want you back. Please consider. But basically, what Dylan sort of set up was that we're able to take this length of the sediment trap transect and then put in the context of the jetty length, right? Extract that QX component and then integrate that same distribution that we showed, but over the jetty length itself. And so to show you, a quick plot of what we got from some of the initial runs of this. So remember, this data set was collected where the wind magnitudes were more or less around the same, as I mentioned, about 0.3 meters per second variability from fastest to slowest. And so, but that wind direction was shifting around quite a bit. So looking at this plot, we have our shore normal wind direction along our x-axis. So 0 is a wind coming perfectly onshore. And then as we work out towards 60, we're getting to higher oblique angles. And then we have our sediment transport rate that's annualized in cubic meters per year on that y-axis. And then I just went ahead and added in, sort of some text box giving you clues to how many cubic meters per year is represented by each one of those dots. And so we see is, at least at this location, that wind direction plays a dramatic role in terms of your annualized sediment transport into that navigation channel. We recently fit in Port Mansfield experiment 2, as well as the third experiment. There are some interesting edge cases that are coming up with the method, but we're working through those currently. But regardless, though, this showcases that not only where you're at on the transect matters in terms of quantifying that aeolian flux, but at what wind direction that flux is arriving from could also be a significant factor in terms of trying to better quantify what that aeolian component is within your system. Okay, so next steps from the aeolian side of the equation is to continue processing the results from the second and third experiment. Year to date, we have over 1,500 aeolian sediment transport rates quantified. The nice thing about using sediment traps is I have the receipts. I have all those sediment samples. So, we're sitting on quite a bit of data and we're really excited to take it to the next level and see what we can do in terms of hindcasting and forecasting, right? I think this is what gets at the heart of a lot of O&M operations and trying to create a better tool, right? Is how can we take this field data from one point in time and then, use it to its full potential in terms of informing, when more dredging might need to occur or, if there's something we can do to prevent some of that aeolian transport. And then lastly, I think Dr. McPherson might talk about this a little bit more as well, is that we are also utilizing this data and kind of leveraging it to really refine the SBAS aeolian sort of working that's going on. So, we have all this field data, let's use it to better inform some other ongoing projects. And so with that, I'll pass it over to Dr. McPherson.
Thanks, Pete. So initially, this part of the project was looking at mostly the aeolian contribution to channel shoaling, but we were informed by the Galveston district that they were planning to dredge the inlet, and so we jumped at the opportunity to do some kind of pre and post dredge studies in order to essentially better understand how this shoal reforms and how the inlet hydrodynamics change as that happens. So they actually just finished dredging. They dredged from February to April of this year. This picture is of the dredge in the inlet. They're pumping the dredge material to the downdrift eroding north side, which is pretty customary here. So we did a pre-dredge bathymetric mapping campaign with the district, and we deployed hydrodynamic instruments, and we got some surficial grab samples. So this is the pre-dredge bathymetric surface. We had the Rio Grande Valley office of the Galveston district go far beyond the normal bounds of the channel surveys to better capture this shoal as it's fully formed, fully shoaled in. And so they are, I think, out there right now doing the first post-dredge mapping campaign. And then we have in this map, I've marked a channel and an ocean location because before the dredging, we went out and deployed two SOFAR spotter buoys. These measure waves and water temperature. And then we also have a bottom-mounted Doppler current sensor to measure point measurements of bottom currents in the inlet and just outside the inlet. Due to some logistical constraints in the field, the pre-dredge deployment was unfortunately pretty short, but we felt it was important to get whatever pre-dredge data we could because dredging is surely going to change the inlet hydrodynamics. And then at the end of this month, we're going to go back and redeploy these buoys in the same locations and see how the hydrodynamics have changed with the shoal gone. So this is some really preliminary data from the channel buoy, which I've added a little map. I don't know if you can see it, it's kind of small. But on this left-hand side, we have some bulk wave parameters from the channel buoy, significant wave height, and then I've marked in red text, we had a front move through the system. And so we're getting pretty large, significant wave heights even in the channel, which is interesting. And then we have peak and mean wave period. And we're seeing some really long period swell to infragravity type waves that I think might bear further investigation. And then on the bottom, we have peak and mean wave direction. And on the right-hand side, we have those bottom currents from the bottom-mounted current sensor. And this is the same data, but from the ocean buoy. Again, we have significant wave height. I've marked where the front moved through. It actually tossed this buoy onshore, which is why this deployment was so short. But then again, we have peak and mean wave period and peak and mean wave direction. And on the right-hand side, again, we have those bottom currents. We collected some grain size data from the inlet and just outside of it with a Ponar grab sampler. And these are the median grain sizes. They're consistent with previous samples collected in 2018 from the King Jr. et al. Study, where they were focusing on Brazos Inlet, but they took a lot of samples throughout Laguna Madre. So our next steps, as I mentioned, were post-dredge hydrodynamic instrument deployments and doing some more repeat mapping as that shoal reforms. But I'd like to compare our data that we're getting to the unpublished 2022 field data branch deployment data and that King Jr. et al. 2018 data. Thank you to Richard Stiles for sharing all of that with us. I'd like to investigate these really long period waves because infragravity waves have been shown to be a closure mechanism in shallow tidal inlets like this. The velocities under those waves can exceed tidal current velocities and increase instantaneous sand fluxes up to 2 orders of magnitude. They tend to be blocked by outgoing ebb currents, so they tend to come in during flood tide, which means you tend to get a net influx of sediment and therefore inlet closure. And then looking at the effects of these seasonal winds and water levels, as we mentioned, this is a heavily wind-dominated system. Seasonal winds set up circulation patterns in Laguna Madre so that there's net inflow into Port Mansfield in the summer and then net outflow in the winter. And the King study found that flow can almost be continuously in or out for like days to weeks at a time. It basically is shutting off the tidal currents because the inlet's so small. So that's interesting. I want to take a look at that. Also, dredging by definition increases the water depth, which might allow more of these really long period waves into the inlet and kind of increase this closure mechanism. And those seasonal winds also can increase water levels at one end of Laguna Madre. So kind of some next potential steps for the subaqueous part of the study. And then kind of in conclusion for everything for this talk, aeolian sediment transport can be a significant contributor to problematic channel shoaling. The sensitivity of your inlet to these processes is really dependent on grain size, your wind climate, and definitely your shoreline angle. Wind direction has a direct impact on sediment transport rates. As I mentioned, we have some ongoing hydrodynamic data collection. We're going to include a lot of this data as test cases into the CIRP sediment budget analysis system toolbox. We're working on that right now to kind of improve the aeolian estimates to your sediment budgets. And because of all these things we're finding at Port Mansfield Inlet, we think it's really important to study both the subaqueous and subaerial mechanisms of your channel shoaling wherever possible. And with that, we have some references. Again, shout out the CHL field team. As Pete mentioned, this is a very difficult field site to get to. This is the field team walking across about a mile of jetty, carrying very heavy equipment in August in Texas. So huge shout out to them. It wouldn't have been possible without them. And also to the Rio Grande Valley field office. And they're shown there with the boat on the top picture. They always go above and beyond. They're awesome to work with. Again, couldn't have done it without them. So thank you to them. And then with that, we'd be happy to take any questions.